law of conservation of energy states that energy can't be destroyed nor created. In a motor, the spinning motion is caused by the electrical energy being converted into mechanical energy. Current passing through the copper coil creates a magnetic field. The neodymium magnet is placed directly under the coil. It has its own magnetic field to refer to Faraday's law of induction. This is one thing we made sure to do in trial 1. The faces of the coil become its north and south poles. Opposite poles attract and like poles repel. The spinning motion is created because the neodymium magnet becomes attracted to the coil's opposite pole while repelling the like pole. To display the operation of the motor alternatively, the neodymium magnet applies a force on the current that flows through the coiled copper.
This is our first attempt at the motor, which didn't spin at all. The major issue that we had was the distance between the motor piece and the magnet. The magnetic field strength is inversely proportional to the square of the distance, so the further the magnet is, the weaker the motor. Additionally, the base is not stable or balanced, which makes it so that there is still some resistance even if the motor spun. In trial 2, we reduced the distance between the magnet and the motor, which made it so that the motor interacted with the magnetic field.
The issue observed in this trial was that the copper coil didn't complete full rotations, rather it just rocked back and forth. A reason that we found for this was that if, for example, the neodymium magnet's north pole was facing upwards, it attracts the south pole of the copper coil while repelling its north pole. However, once the copper coil's south pole is close to the north pole of the neodymium magnet, it just stays there, only rocking around this equilibrium position.
Trial 3 is where the motor finally starts spinning. However, the spinning isn't consistent, and the wire used here isn't the wire we plan to use for the final. Also in this trial, the connection wires are messing with the stability, causing the paper clips to slant. The overall design is the same as the previous one, but this is our first attempt with the red wire. This was unknown at the time, but the red wire's insulation came off on the center of the coil, causing the motor to short circuit and not do full rotations. This was the final design. We fixed the insulation problem of the coil by making a new one. This allowed for the motor to actually spin. We moved the connection wires to the bottom of the paper clips to get a more stable ground. We also used stronger tape for this. Due to the motor being more stable, we were also able to make it more consistent, which can be seen in this video, in which each time I take the battery off, the motor stops, and when I connect it, it spins again.
The highest RPM of the motor on the final test day was 6,700. Our coils should have more rounds of wire to increase the strength of the magnetic field because each of these coils has their own magnetic field, resulting in more field lines and thus a stronger electromagnet. Our coils should be tightly wound and uniformly wound to have a better transfer of energy by reducing any air gaps or space. Also, having these close together can result in closer field lines, resulting in a stronger field for both electric and magnetic fields.